Welcome back. All right, so we talked about kind of from small to large, cinder cone volcanoes, a little bit bigger composite volcanoes, those are very dangerous. Bigger shield volcanoes, let's start there. So, large, but very broad. They look like shields from above. If you're looking at like at a satellite image straight down into these, they're very round, kind of very gently domed up, almost like a shield. Like think about Captain America's shield. The lava that pours out of these types of volcanoes is very, very thin, very runny, has a low viscosity. There's not a lot of buildups, not a lot of pressure. So these aren't explosive. So the lava that kind of pours out very runny comes out of the vent and kind of just spills out in all directions, which helps to create this very kind of not very steep shield kind of domed shape. They build up slowly over time. Hundreds of eruptions can be common, and they erupt over and over, creating many layers of lava. Again, these are not likely to explode catastrophically whatsoever. The Hawaiian Islands, Mauna Loa, Mauna Kea, Kilauea, all great example of these shield volcanoes in which basalt is common. Basalt, mafic, igneous rock, that mafic material coming from the upper mantle, a little bit heavier material, darker in color, but it also is very low in silica, therefore it has a low viscosity. It's very runny. The more silica, the more sticky, the more explosive a volcano could be. So again, kind of a cross section, not very steep at all. Not very steep at all. But they can be very, 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 very wide. Again, lava flows. You can get some material lava fountains, very beautiful looking eruptions, but they're not going to just kind of explode violently like a composite volcano would. So, Mauna Loa in Hawaii, again, very big, but not very steep. Mauna Kea, again, very big, just not very steep. Kilauea, again, very big, just not very steep. So here's some footage of Kilauea eruption. Please make sure you're watching that. Additionally, a number of semesters back, a student of mine did an honors project to help you remember the different types of common volcanoes, cinder cones, composites, shields. It can be helpful. It can help you learn these things, get these things stuck in your head. But then there's one more type of volcano. These are the biggest volcanoes. These are super volcanoes. Not any volcano, a super volcano. The reason I don't include these in the common types of volcanoes is they're just extremely rare in Earth's history. Currently, there are 7 active supervolcanoes on land. 3 of those are in the United States, which is why we talk about them, because they can be important. They are unimaginably large. Most of where you would find a supervolcano is going to be underground, so you don't really see too much on the surface. More on that in just a minute. So the classification of a supervolcano is that when it does erupt, it must erupt a volume of 240 cubic miles of material. Let me just do some math here. Let's see, what is the cube root of 240? Let's see here. 240 cube root. So that would be a cube about 6 miles on all sides, full of material. That's how much material is erupted out of a supervolcano at a minimum. At a minimum. For reference, Mount St. Helens, which was a large eruption, you saw that in those videos, only emitted 0.29 cubic miles of material. So supervolcanoes, at a minimum, have to be about 800 times larger than the eruption of Mount St. Helens. Just incredibly large. There's a very large magma chamber underneath the ground that erupts almost entirely in one catastrophic explosion. Creates a huge hole, a huge depression. So you have this big magma chamber underground. We'll look at a diagram in a minute. It erupts everything it can. Then you just have this big open void, and then whatever was above it just kind of collapses in, and that structure is called a caldera. Rhyolite is very common in supervolcanoes. So rhyolite, felsic extrusive igneous rock, meaning high in silica, so very high viscosity, so very, 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 very sticky. so sticky that it doesn't really want to make a volcano. It doesn't really want to come out. So you just get this very sticky, huge plug of pressure underneath. And when there's enough pressure behind it, and it goes, again, bigger than any composite volcano. These are super volcanoes. So a little diagram of how it works. Get this kind of big magma chamber growing. These magma chambers are so big, they just kind of tend to lift the whole ground underneath it. Not make like a little mountain. They just lift the whole ground, parts, chunks of whole states. They just lift it right up. And then eventually, once that material, again, erupts and there's no longer material underneath there, the surrounding area above it collapses in, forming what's called a caldera. Here are the locations of the at least known supervolcanoes. Again, 3 of them right here in the U.S. Not only that, pretty much right around us. Right around us. So we got one in Wyoming and in California, right over in New Mexico area, and Arizona's right in between these 3 bad boys. But there's one in Russia, Japan, Indonesia, New Zealand, some of these different super volcanoes. So one of the more famous supervolcano, the Yellowstone supervolcano. There's documentaries about it. You may have just randomly heard about this somewhere at some point in your life. So this is the largest supervolcano in North America. It's right below Yellowstone National Park. The reason this is here is because Yellowstone sits above a hot spot. More on that in a second. A hot spot is just this weird, anomalous spot that's hot in the mantle that's kind of heating up the material above it, melting the material above it. So you get this kind of, due to convection, this weird plume of heat kind of just right below Yellowstone. And Yellowstone National Park is sitting right on top of that. This area has actually erupted catastrophically 3 times. 2.1 million years ago, 1.3 million years ago, 640,000 years ago. And if you do the math, that's about every 700,000 years. So if the last one was just under 700,000 years ago, we're kind of getting due, historically speaking. So this is the area under Yellowstone National Park that is seeing ground level change. So kind of a rate of change, how fast the ground below is kind of being risen up. And you can kind of see this bullseye structure here. So underneath there is that magma chamber that's pushing up below the ground. And using different instruments, what this image is showing is that this area is being kind of raised up. It's kind of being raised up. You can see that this bullseye area is just about, I don't know, 20 miles wide, maybe a little bit less. And that's the magma chamber. Absolutely huge. Absolutely huge. So again, here's another kind of cross section of what you see. Kind of this, again, rhyolite. Again, very sticky stuff. It's preventing even some basaltic magma from behind it. So you're getting a lot of pressure behind this, kind of pushing up this whole area. So the Yellowstone area does already have a number of calderas from past eruptions, but now this material from below is kind of pushing it back up, called a resurgent caldera, resurgent dome, because now it's building back up again. In Yellowstone, it's also famous for geysers and hot springs, all of those being fed from the heat of that magma chamber. This graph shows the number of earthquakes in the Yellowstone area from 1975 to 2000, and you can kind of see how the number of earthquakes are kind of on the rise. So is an eruption imminent? Is an eruption imminent? Maybe. Ground's rising. Earthquakes are rising. Maybe. This diagram shows the potential if Yellowstone were to erupt. It's in this kind of northwest corner of Wyoming. If Yellowstone would erupt, everything in the circle, total destruction. Total destruction. Gone. When Mount St. Helens erupted, which was kind of over here, there was, maybe about 5-10 miles of total destruction. This is half the country. Just done. Just done for. Thankfully, supervolcanoes are not common. So, reflecting back, we have these different types of volcanoes which kind of erupt gently, erupt violently, catastrophically, more lava and gas, more kind of debris and ash. So what is all of that based on? Well, the diversity in volcanoes and eruptions, so how and where the magma formed is kind of where it starts. That's where it begins. And that's due to plate tectonics, the different boundaries, what's going on there, hot spots, etc. So how and where the magma formed, where did it melt from? Did a mantle plume melt the mostly solid mantle material? So the mantle plume melt the crustal material? Did it melt somewhere kind of in between? So where the magma formed, and how and where the magma formed then dictates the chemical makeup of that magma. The chemical makeup determines the viscosity of that magma. Less viscous is more runny, so gentle eruptions, shield volcanoes, cinder cones, or a more viscous molten material creating explosive composite volcanoes or catastrophically explosive supervolcanoes. As you get into your kind of crust, mantle, or crustal material, intermediate or felsic melt material. And then the viscosity of that molten material determines the type of volcano created and the associated hazards. So it all starts with where the molten material comes from. Again, kind of in this lower kind of area, which is still the upper part of the mantle. Remember, the mantle is still mostly solid. So it's these mantle plumes melting this mostly solid material. So from the upper mantle, you're getting more basaltic magma. From the crust, you're getting rhyolitic magma. And if you're kind of in between the two, you're getting more andesitic magma. So that, where the material melts from, determines the chemical composition, which determines the viscosity, which determines the volcano type and eruption type. So basaltic magma, low in silica, meaning low viscosity, very runny. Gas does not tend to get stuck in it, so it's not explosive. It's not kind of catastrophic when these volcanoes erupt. And acidic magma, kind of in between the upper mantle and the crust, it's an intermediate amount of silica, so an intermediate amount of viscosity. It starts starting to get sticky, starting to have some gas content, so they can and do erupt violently, and they are a common type. And you have rhyolitic magma, high in silica, therefore very sticky, high viscosity, which tends to trap a lot of gas, and when those do erupt, they erupt catastrophically, super volcanically. Kind of rare though, thankfully. So let's go ahead and pause there. We talked about different types of volcanoes. Now, when we come back, we'll talk about volcanoes in Arizona? What? I'll see you back here in just a minute.